So now I want to talk about paramagnetism and ferromagnetism. With paramagnetism, what happens is you apply a magnetic field to a material. So you got some material here and you apply a magnetic field to it and you induce a magnetic field in here which actually ends up amplifying your magnetic field. And so this is what we call paramagnetism. And again, what's happening is you're interfering with all the random motion of the dipoles in there, and they are lining up and amplifying your field. Now, not every material does this. All materials will introduce a little bit of diamagnetism. Only certain ones that have sufficient just loose electrons are moving around, isolated electrons, that can do this. You're not going to get this really with like an ideal gas or something that has all electron shells full, in which you have, pretty much electrons going both ways and everything, and you're canceling everything out. So here you're amplifying the effects, and so this is stuff like in the middle of the periodic table that does this, in which you have lots of electrons available. And so what's going to happen is that you end up amplifying the magnetic field, and we define something called the magnetization. The magnetization here is defined to be the measured magnetic moment, so the mu that you're measuring divided by the volume. Okay, so that's your magnetization. The magnetization turns out, interestingly enough, to be related to the applied magnetic field. So if you increase the magnetic field, then you tend to increase the magnetization. And so the magnetization here, there's something called magnetic susceptibility. And the magnetic susceptibility is related to the magnetic field strength. Okay, magnetic field strength, we define that to be H, and that's the magnetic field over mu naught. And the magnetization vector is going to be the magnetic susceptibility times the magnetic field strength. So that's your magnetic susceptibility. That's a lowercase Greek chi symbol. Okay, and so the magnetization is now going to be what you get here, and so the total magnetic field out here is now going to be amplified. It's going to be equal to mu naught times the magnetic field strength that you're applying plus the magnetization, which is what's happening from your own, what's happening to the material itself right here. And that depends on the susceptibility. So in other words, the magnetic field, if you do a little algebra right here, the magnetic field is going to be mu naught plus 1, mu naught, it'll be mu naught times chi plus 1 times the magnetic field strength. And so that would be how you would actually work out all the details of this. Okay, now we're not going to go quite that in depth in this, but you should know, for example, that you turn on this magnetic field, and for certain materials you actually get a stronger magnetic field. And so that is the example of magnetism. Now, the actual equations related to paramagnetism are that the magnetization here is, again, we talked about the magnetic susceptibility, but that is related to a constant, a Curie constant, times the external magnetic field divided by the temperature. So this is not period, that's temperature, and that's measured in Kelvin. Okay. Now this gives you an approximation here, so that if you were to graph this, you would get something kind of like that up to a point. At some point, the Curie law doesn't hold, and it sort of bends over and stabilizes. You end up with a maximum possible magnetization right there. And the other thing that happens is that if T gets too big, it also doesn't apply. So this works, for a range of temperatures, but if you increase the temperature to a certain point, then it starts to fail. And so this is paramagnetism. The other thing I want to talk about is ferromagnetism. Ferromagnetism occurs to things near the middle of the periodic table. So if you imagine things that are, like in here somewhere, remember, as you're putting the electrons into the atoms, you're adding electrons. No two electrons can be the same quantum numbers, and so you're getting more and more of these unpaired electrons going around, and you're increasing the total magnetic susceptibility, really, because what's happening is that you are getting more and more little magnetic dipoles. Now, they tend to be all different directions, but because you've got several in the same atom, they start interacting with each other, and they will actually line up the individual atoms here, and the individual atoms might be randomly oriented, okay? But just like with paramagnetism, if you apply a magnetic field, then they tend to want to all go line up with that, and that increases your total magnetic field. So for ferromagnetism, this sounds very much like paramagnetism. So everything pretty much works the same way, and so the total magnetic field is going to be your external magnetic field plus the magnetic field due to the magnetization that you've just implemented in here. And so now the total magnetic field is stronger. Again, this sounds very much like paramagnetism, except with paramagnetism, when you turn off the magnetic field, everything goes back to random orientation. When you turn off the magnetic field with ferromagnetism, then what happens is you end up with like atoms interacting with each other, or neighboring atoms interacting with each other, and creating these little magnetic domains. And the magnetic domains are have orientations that are in particular directions. If enough of them average out going this way, that means you retain a magnetic field even after you turn off the external magnetic field. So, if we were to do paramagnetism, then what would happen is, if the magnetic field that you get versus the applied magnetic field, does this and that, and so it goes back and forth. Okay. But for ferromagnetism, then what happens is you apply a magnetic field, you get a magnetic field. Then you turn off the magnetic field, and what happens is you have a residual magnetic field. So that means that you turn off the magnetic field, it's residual. Okay, so you still have a magnetic field when you turn it off. Okay. Well, then you reverse the magnetic field, and then you turn it off, just like this, and then turn it on like this, and then comes back. Okay. And so what's happening is that you get this hysteresis effect in here. And so even if the applied magnetic field is 0, you would still have a residual magnetic field left over from what it had been. You would have to reverse this magnetic field in order to bring the magnetic field down to zero. And so that means we would say that it is a permanent magnet. Okay, so because you turn off the applied magnetic field, the magnetic field drops but does not go to zero. You have to reverse the magnetic field in order to cancel out the magnetic field. If you keep reversing it even stronger, then what happens is you end up with a reverse magnetic field. You turn it off and it's still reversed magnetic field. And so you have to, again, put a forward bias magnetic field on it to bring it back to zero. So this is basically how you would demagnetize something. Okay, now, in order for this to work, all the magnetic domains have to be oriented in similar directions. If they're totally randomized, you do not keep your permanent magnet. Well, how do you disorient them? Okay, so here's your magnet. You can disorient it two ways. One is just physical shock. Okay, so what you can do is you can have, just bang on it, and that will gradually demagnetize it. Okay. Because physically you're shaking all these magnetic domains and you're disorienting them. Now, oddly enough, if you have a weak magnetic field and these things are pretty randomly oriented, then if you bang on it, you can actually knock them around and they will tend to line up with that magnetic field. So now there's always a magnetic field. Earth has a magnetic field. So if you bang on a piece of iron with a hammer in the presence of Earth's magnetic field, it will gradually become very weakly magnetic. And so you'll make a weak magnet that way. The other way that you can kill this magnetic field is heating it up. So if you heat this beyond a certain temperature called the Curie temperature, then what happens is thermally all the atoms get disoriented and they start pointing in all different directions, and then when you cool the temperature, it's no longer magnetized. So that Curie temperature is this key. If you want to get rid of a permanent magnet, you can either heat it up to the Curie temperature or you can bang on it. When you bang on it, you don't really get rid of all the magnetism. To get rid of all the magnetism, you have to reverse bias it. And so for certain applications, for example, warships, you don't want to be magnetized necessarily because a submarine that's magnetized can be picked up with a magnetometer. A magnetic warship can set off a magnetic mine, and so you don't want that. So you want to demagnetize it. Call that degaussing the warship. And so, but warships, being warships, they have lots of banging going on them. And so when that happens, they tend to become slightly more magnetic. Or at least this was the case back when warships were primarily made of steel. We have a lot of other materials we use today. But if you have a steel warship, it tends to become weakly magnetized over time, and you want to degauss it now and then. So this is kind of a rough overview. We're not going to go into super depth this semester with all of this, but this is a very rough overview of magnetism in matter. We have diamagnetism, paramagnetism, and now ferromagnetism. And so this gets a little bit complicated. We're not going to go into this as in depth as we could go into. That involves mathematics a little beyond the level of this class. We are just getting the high points of the basic concepts of paramagnetism, ferromagnetism, and diamagnetism, along with other magnetic properties in matter.